this video, we're going to discuss hydrogen bonding. So hydrogen bonding has two requirements. We need to have a hydrogen atom covalently bound to either an oxygen, nitrogen, or fluorine atom, and we have to have a lone pair on an adjacent or a neighboring oxygen, nitrogen, or fluorine atom. So there are two requirements for the hydrogen bond. I have examples A, B, and C that we'll go through here. These are several of the permutations that you could encounter looking at the hydrogen on an oxygen, nitrogen, and fluorine, and a lone pair on an oxygen, nitrogen, or fluorine. Let's look at example A first. Here we have an oxygen with a hydrogen covalently bound to it. We also have another molecule over here, a nitrogen, that has a lone pair. So thinking about the hydrogen bond and this bond polarity to begin with, the oxygen, because it's more electronegative, has a partial negative charge, and the hydrogen has a partial positive charge if we assign bond polarity to that oxygen-hydrogen bond. At the same time, the lone pair on the nitrogen, we would expect to have a very strong partial negative or even negative charge associated with it. The hydrogen bond is the interaction between this partially positive region and this electron-rich lone pair. So I'm going to draw the hydrogen bond here as a dotted line to indicate that type of interaction between this partially negative region or very negative region and this partially positive hydrogen attached to an electronegative atom. So here's one possible permutation of a hydrogen bond. Let's look over at example B. Here we have hydrogen attached to fluorine. Again, we have an oxygen with a lone pair. So our hydrogen bond interaction is here, and we're thinking about this partial negative and this partial positive interaction associated with those. Example C, here, if we look at the bond polarity, we'll have a partial positive due to the hydrogen and a partial negative here. That's our hydrogen bonding interaction there. So the key to remember is that for a hydrogen bond to form, we need a hydrogen atom on an oxygen, nitrogen, and fluorine, and on the neighboring atom, we need a lone pair on an oxygen, nitrogen, and fluorine. We don't necessarily need to have both oxygen with the hydrogen and oxygen with the lone pair. We could have a mixture, as I've tried to illustrate here. Another thing that's important to think about when thinking about hydrogen bonding is the molecule able to hydrogen bond with other molecules just like itself, or is the molecule only able to hydrogen bond with other things like water? So let's compare ammonia to formaldehyde. Ammonia contains both of our requirements for hydrogen bonding. It has a nitrogen with a hydrogen attached to it. It also has a nitrogen with a lone pair. So ammonia can hydrogen bond to other ammonias. So here's our hydrogen bonding interaction. It could also hydrogen bond here. We could have a lone pair. So ammonia could hydrogen bond with itself or with another ammonia molecule. Formaldehyde, on the other hand, only contains one of the requirements. It has an oxygen with a lone pair. The hydrogens in this molecule are actually connected to a carbon. So if you compare the electronegativities of those two atoms, this is not a polar bond, so we don't generate a partial positive charge area here, so we will not hydrogen bond with that hydrogen. We do form a hydrogen bond with, let's use water as an example. We would expect to form a hydrogen bond there. So formaldehyde can form hydrogen bonds with water, but formaldehyde cannot form hydrogen bonds with itself. Contrast that with ammonia. Ammonia could form hydrogen bonds with itself. Ammonia could also form hydrogen bonds with water.